Okay, so last time we were talking about joint distributions, and just to kind of quickly remind everyone, kind of like the big theme right now is joint, conditional, and marginal distributions, and everyone needs to get comfortable at how all those concepts relate. So there's three different types of things: joint, conditional, and marginal. And we were talking about joint and marginal distributions last time. Not so much about conditional distributions, but it's analogous to stuff we've already seen about conditioning. So those are the three key words: joint, conditional, and marginal distributions. Okay, so at this point in the course, we pretty much have all the tools we need for working with one random variable at a time. Okay, but there's much more that we need to study about what happens when we have two random variables, or a sequence of random variables, things like that, a sum of 1,000,000 random variables, things like that. So we're going to be talking a lot about what happens with lots of random variables at the same time. And that's why I keep emphasizing that everything is cumulative here, because if you have trouble with one random variable and its CDF, then understanding two of them at the same time is going to be really difficult. Okay, so so we always have a joint CDF if there's two of them. I'll just write down what it looks like: f of x, y. So joint CDF would be this for two random variables. But of course, if we had 1,000,000 random variables instead of two, I'm not going to write this down. I could write x1 through x 1,000,000, and then x1 less than or equal little x1, and so on, and 1,000,000 of them. So this extends to as many as you want, but it's just easier to write it down and think about for two of them. But it's more general than this. Okay, that's the joint CDF. That always makes sense. They can be discrete, continuous, mixtures of discrete and continuous, or anything. In the continuous case, then we have a joint PDF, which I talked a little bit about, but I don't think I wrote down how to get from the joint CDF to the joint PDF. So then we have a joint PDF, and it's analogous to the one-dimensional case, where in the one-dimensional case we take the derivative of the CDF to get the PDF. In this case, we take the derivative, except that it's a function of two variables, so we're going to take two partial derivatives. And so I would write it as d squared of d squared dx dy f of xy, which looks complicated, especially if you haven't seen partial derivatives. But there's even if you had if you haven't ever done partial derivatives for, there's nothing really to worry about with this. All it means is take the derivative of this. This is a function of two variables. Take the derivative with respect to y, treating x as a constant, right? So if you can do derivatives, which I'm assuming you can pretend x is a constant, and then take the derivative with respect to x, holding y as a constant. And there's a theorem in multivariable calculus that says that under some mild conditions, it doesn't actually matter if you take the partial with respect to y, then with respect to x, or with respect to x and then with respect to y, you'll get the same thing. So this is, again, analogous to the one-dimensional case, and the joint PDF is what this is not a probability, that's a density. That's what we integrate to get a density. So integrate this. If we want to know, what's the probability that xy is in some set A, then that's just going to be the integral over that set A of the density. If you haven't done double integrals before, again, it's no big deal. Just integrate with respect to x, holding y constant, then integrate with respect to y. Basically, the only complicated thing is figuring out the limits of integration. So I just wrote double integral over A, because A could be any region in the plane. So if we had something like, if A is this blob, that may be a hard problem to do this integral. What does it mean to integrate over the blob? I mean, that turns into a nasty multivariable calculus problem. That's not something we care about for this course. It's just a nasty calculus problem. It's not an interesting probability problem. Okay? So the more interesting case for our purposes would be if it's let's call that A1. Now here's the A we actually want. If it's a rectangle, then that just means, then this double integral just means integrate, you know, x goes from here to here, y goes from here to here. So it just literally is just the integral of the integral. So it's no different from doing two integrals. So you don't have to worry too much about the blobs. There's only one case where we might care about the blobs in this course. That's when we have a uniform distribution over some region. So at the very end, I'll come back to this. At the very end, last time we were talking about a distribution that's uniform over a square or uniform over a circle, that kind of thing. And in that uniform case, we can interpret probability as proportional to area, okay? So in the uniform case, probability is proportional to area, and then I could say, well, I'm just going to do something proportional to the area of the blob, and at least I can think more geometrically, okay? So, but anyway, you know, conceptually, it's analogous. The joint PDF is what we integrate to get the probability of x, y being in any particular set, right? In one dimension, we'd say, what's the probability that x is between -3 and 5, right? We want an interval. And here we want the probability that's in some region. But, you know, the rectangular case is going to be the nicest one, okay? So those are joint distributions, and I talked a little bit last time about how to get the marginal, and it's very straightforward. Marginal PDF of x. To get the marginal PDF of x, we just integrate out the y. So we just integrate -infinity to infinity f of xy dy. Notice that by doing this, we'll get something that's now a function of x is just treated as a constant here. We're integrating over all y. This is no longer going to depend on y, because you're integrating over all y. It becomes a dummy variable. Similarly, you can get the marginal PDF of y by integrating dx, okay? And this is just completely analogous to saying, you know, doing a summing over the cases, right? It's just saying we want x to be this little x and y has to be something, so we just integrate over all possibilities, and okay. So that's the marginal. So that's called marginalization, that we marginalize out the y, then we get the marginal of x. We integrate out the y, we get the marginal of x. It's just terminology for something very simple, just integrate. If we did a double integral, so if we then took this thing and integrate this dx, we should get 1. And what that says, one way to think of it is to say, if we let A be the entire plane, like everything, we'd better get 1, right? Otherwise, it wouldn't make any sense. The other way to think of it is, this is supposed to be the density of x just viewed as x in its own right. So if we integrate this dx, we have to get 1. Otherwise, we did not find a valid marginal PDF. So that has to integrate to 1. May as well write that down just for emphasis. The double integral equals 1. And it's always -infinity to infinity, -infinity to infinity to start with. It might be that this is 0 outside of some region, and then we could restrict it further. But we could always write it like this at first, and then we should be careful about where is it 0, where is it non-zero. So that's a marginal. Let's do the conditional distribution. So we want conditional PDF. And this should be easy to understand and remember because it's analogous to conditioning we've done before. So let's say we want the conditional PDF of y given x. Well, we would just write that as f. Sometimes we'd put a subscript of y given x just for emphasis, and sometimes we may leave out the subscript just because it's clear from the context. Conditional PDF, it's just, you know, it's think of it as the PDF where we get to pretend that we know what x is. We get to observe what x is, okay? Given that information that we now know the value of x, what is the appropriate PDF for y? Well, we could think of that as being the joint density divided by the marginal density of x. What I just wrote down just looks like the definition of conditional probability, right? The probability of this given this is the probability of this and this divided by the probability of this thing. Now, these x and y are representing numbers, not events, okay? But it looks the same as the definition of conditional probability, and you can derive this from the definition of conditional probability, where basically what you would do is say our event is that y is either take y equal to y, or if we're worried about probability 0, say like y is extremely close to y. That is, we let y, capital Y, be in some tiny little interval around little y, and find the conditional probability of that given the value of x. And it's completely analogous to conditional probability. So this says that we can get the conditional just by doing the joint distribution, joint density divided by the marginal density. We could also do something that looks like Bayes' rule. That is, what if we want the conditional PDF of x given y? Well, we go x given y, f of y. I'm just writing down something that looks like Bayes' rule. That looks like Bayes' rule, right? I swapped the x and the y, and but instead of probability, I'm doing the density, and then density. Completely analogous to Bayes' rule. The proof is really use Bayes' rule and then take a limit. And so this should be easy to remember. And the numerator is the same. Another way to say this is that to get the joint density, we can take one of the marginals, then times the other conditional, right? That's like, if we're pretending it's probability rather than a density, it's like the probability of this y value times the probability of the x value given that y value. So everything is analogous to Bayes' rule and the discrete case. All right, so those are just the basic concepts we need for that. And I should mention again that how to think of independence. So again, this is the continuous case. X and y are independent if well, the general definition is in terms of CDFs, but it's usually easier to work with the PDF than the CDF. So usually the best way to think of it is independent means that the joint PDF is the product of the marginal PDFs. And that has to hold for all x and y. It's not too hard to show that that's equivalent to having the CDFs factor, because basically, if the CDFs factor, you could take the derivative, this derivative thing, and you'll get this. You could take this thing and integrate and go back there. So it's basically equivalent. And intuitively, it should be equivalent. All right, so let's come back to this uniform example, because I wanted to write, what's the conditional. We wrote down the joint PDF last time. I'll remind you. That is, we had the distribution that was uniform on a circle, or inside the disk. So uniform in the disk, which is x squared plus y squared less than or equal to 1. And we're picking a uniformly random point, maybe there. Uniform means that probability of some region is proportional to area, okay? So therefore, so one nice thing, when we have problems that involve a uniform distribution on some region in the plane, we can actually think of probability in terms of area, or at least it's proportional to area. So the joint PDF we did last time is just 1 over pi. It's 1 over the area, because that will make it integrate to 1 within the circle, x squared plus y squared less than or equal to 1, and 0 outside. Okay? But just for practice, let's get the marginal density of x and then the conditional density, x given y or y given x. So, and by the way, this may look like they're independent because this doesn't, this looks like somehow it factors as a constant times a constant, but x and y are not independent here, right? Because if x is very close to 1, then it's constraining the values of y, so they're definitely dependent. But you have to be careful about things like that, because if you just only look at the 1 over pi, it looks like they might be independent, but the key thing is that they are constrained together to be, right? So this is saying that x and y are actually closely related. But if you only look at this part and ignore this part, you might think they're independent. All right, so let's get the marginal. F of x equals fx of x. All we have to do is integrate out the y. So we're going to integrate the joint PDF, which is 1 over pi. As long as we're careful we're going to integrate this thing dy. The only thing we have to be careful about is the limits of integration. Now, this is only valid when x squared plus y squared is less than or equal to 1, which is the same thing as saying that y squared is less than or equal to 1 minus x squared. And that tells us that y has to be between minus square root of this and plus square root of this. So we're going to integrate from minus square root 1 minus x squared to square root of 1 minus x squared. So the main mistake with this kind of problem is messing up the limits of integration somehow. We have to be very, very careful with limits of integration. You're not actually ever going to have to do any difficult integral in this course, but sometimes you have to think carefully about the limits of integration. Okay? So this is just saying these are the bounds on y for which I should have 1 over pi rather than 0 here. Okay? So if you get the limits of integration wrong, then it's just completely wrong. All right, this is a very easy integral. Just integral of a constant is just the constant times the length of the interval. So that's just 2 over pi square root of 1 minus x squared. And that's valid for minus 1 less than or equal to x less than or equal to 1. As a check, we could integrate this thing dx, and how do you actually integrate the square root of 1 minus x squared? You would do a trig substitution. I'm not going to do that integral right now. But you could integrate this thing from minus 1 to 1, use a trig substitution as you just suggested. That's basically going to reduce it back down to the fact that it's based on a circle, and you'll get 1. So, okay, so that does integrate to 1. So that's the marginal PDF. Notice that this does not look like a uniform. So it's certainly false that it's to say that it's uniform between minus 1 and 1. The point, xy is uniform, but the marginals are not uniform, right? And in fact, you can see that this is largest when x is 0, which kind of makes sense, because if you imagine a random point here, then kind of near the center seems like there's more space for stuff to happen. And it seems a little less likely to be out, further out, okay? So let's get the conditional PDF now. So we can either do y given x or x given y, whichever we feel like. Oh, notice that if you want the marginal PDF of y, just change the letter x to y here by symmetry. There's no need to repeat the same calculation. Okay, so let's do the PDF of y given x. So that's just going to be the joint PDF divided by the marginal PDF of x. So it's just going to be 1 over pi divided by 2 over pi square root 1 minus x squared. I just took the joint PDF divided by the marginal PDF, and we have to be careful about where is this not non-zero. I'm thinking of y as fixed right now. It's like we get to observe x, and I want to say, well, what are the possible values of y? Well, for each x, we know that y has to be between minus square root of 1 minus, same thing again. Y has to be between minus root 1 minus x squared and 1 minus root 1 minus x squared, okay? 0 otherwise. So the pi's cancel. And that looks kind of ugly. Well, what would be another way to say what this conditional density is? But you're treating x as a constant. What would you call this thing? Uniform, because notice this only has an x here. There's no y. In general, you would have a y here. There's no letter y on the right side of this equation. So a nicer way to write this would be to say that y given x is uniform between minus root 1 minus x squared and root 1 minus x squared, because this is just a constant for each fixed x. You can here, I wrote this with capital X here. to clarify this notation, when you see this thing like y given capital X, what does that mean? Intuitively, that means just pretend that capital X, we know X is a random variable, but pretend capital X is a known constant because we got to observe it. But you can just think of this as shorthand for saying y given x equals little x. This kind of is a more direct way to write it. That is, we get to observe that big X equals little x, and we're saying that if we know that, then we have a uniform distribution between minus square root of 1 minus little x squared and square root of 1 minus little x squared. But it's a little more cumbersome to write it this way, so sometimes we'll write it this way with capital X, but just treat that as shorthand for this. That just means, given that we get to know what x is, here's the distribution for y. So we're treating x as a constant here. And here we're explicitly calling that constant little x. It's just notation. So, okay, so that says it's conditionally uniform over some interval. Notice that that's the appropriate interval, because as soon as you specify what x is, we know y has to be between here and here. This says it's uniform. So that, similarly, you could do f of x given y. And you can see that they're not independent because, well, one way to see it is f of xy does not equal the product of the marginal PDFs in general here, right? Take this thing and then the same thing with y, multiply them, you do not get the joint PDF. So they're not independent. Another way to say that they're not independent is that the conditional distribution of y given x is not the same thing as the unconditional distribution of y. That is, learning x gives us information. Okay? So, all right, so those are these basic concepts, joint, conditional, marginal. I wanted to mention one more thing that's analogous to the one-dimensional case, and that's what I call the 2D Lotus. And it's completely analogous. So we want to do Lotus where we have a function of more than one variable. So let's let xy have a joint PDF. I'll state it in the continuous case, but you could also do a discrete 2D Lotus if you want. So we have a joint PDF, f of xy, okay? And then just let g be any function of xy. Let's say it's real valued. So this function g takes two values as input and outputs one value. For example, it could just be x plus y, or it could be x squared times sine of xy cubed or whatever, just any function of x, y, okay? A real valued function of x, y. And then we're going to write down Lotus. Lotus tells us how to get the expected value of g of x, y. And it says we do not need to try to find the PDF of g of x, y. We can work directly in terms of the joint PDF. And all we have to do is integrate. It's going to be minus infinity to infinity, minus infinity to infinity, but possibly we can narrow down that range of, I just change capital X, Y to lowercase x, y, and then I use the joint PDF. Completely analogous. So let's do a couple examples. How is this fact useful? So here's an important fact that I already needed this fact once, and we didn't prove it yet, which was like we were talking about the fact that the MGF of a sum of independent random variables is the product of the MGFs, and at some point we need to say E of something times something is E of something, E of the other thing. That's true when they're independent. That's what we need to show right now. So the theorem is that if x and y are independent, then E of xy equals E of x, E of y. That's a very useful fact. we'll come back to this fact later when we talk about correlation. The way we would say this in words is that independent implies uncorrelated. But that's just foreshadowing correlate. Later we'll talk more about what exactly does correlation mean. But when we define correlation, in a later lecture, we'll see that actually says that they're uncorrelated, and so this says independent implies uncorrelated is the way to say it in words. Okay, so let's prove this fact. This is always true. It doesn't matter if they're continuous or discrete or whatever, but so that we don't have to invent a lot of new notations or do a lot of cases, let's just do the continuous case for practice. So proof in the continuous case, well, we're just going to use the 2D Lotus, right? That saves us a lot of effort because when you just see this thing e of x, like x times y is a random variable in its own right, okay? So the first time you see this, you might think, I need to study that random variable. That takes a lot of work. 2D Lotus just says, well, that's just a function of x, y. I'm just going to use Lotus, and it's going to be easy. So e of xy equals, how do we do this? Well, just write down, double integral minus infinity to infinity, minus infinity to infinity, xy times the joint PDF. But since we assume that they're independent, the joint PDF is just the product of the marginal PDFs. So independence means that the joint PDF just factors like that. And that's what makes this actually easy to deal with, because this function has just separated out, like this is a function of x, function of y, function of x, function of y. Very nice. So what do we actually do? Well, what this says to do is take this, I'll put parentheses here to make it a little clearer what this double integral means. That's just the definition of this double integral. It says do this integral and then do this outer integral, right? So you work your way out. When you're doing this inner integral, you're treating y as a constant. So this y, you can stick it right there, and this fy of y, also stick that there. Right, both of those come out. So let's read. That looks a little messy. Let's rewrite that. All I did was to take out the y and the marginal PDF of y, and what's left is the x and the marginal PDF of x. Okay, so I just took them out. Now this whole thing here, that's just a number, right? That just says we took this function and we integrated it over x and we get a number. That's just a constant. So and we know what constant that is, right? That's e of x. That's just a number. So that constant you can pull out of this entire integral, right? It's just a constant. Take it out of the integral. What's left? Integral of y times the PDF of y, that's just e of y. So that's immediately just e of x, e of y. So basically this amounts to, that's e of x times e of y. All this amounts to doing is just taking out things that you're treating as constant and then it factors. Okay, so that's a useful fact, and it would be a nightmare to try to prove this without having Lotus available, but with Lotus, then we could do that pretty quickly. All right, there's another problem I like to do with the 2D Lotus, and that's like expected distance between 2 points. So let's start with the uniform case. Okay, this is, I talk about this on the strategic practice too. You can look at later, but I think this is a useful point for everyone to see this now. So this is an example where we take two uniforms. Let's let them be x and y be IID uniform 0, 1, and we want to find expected distance between them. So this kind of problem comes a lot in applications where you have two random points, and often you want to know how far apart they are. So this is used for various applications. And so one approach would be try to study absolute value of x minus y. Find its distribution, and maybe for some problems we need the distribution. Okay, but in this case I said I only want the mean. So therefore Lotus should suffice for that. So just write down Lotus. So it's a double integral x minus y. And since they're IID uniform, the PDF is just 1. The joint PDF is just 1. So I just have to integrate this thing dx dy from 0 to 1, 0 to 1. Okay? So then the only question, I guess, is how do you integrate absolute value? Well, usually if you want to integrate absolute value, the strategy would be to split the integral into pieces such that you can get rid of the absolute value. Okay, so we could split this up as one piece where x is greater than y. I'll write it this way, x greater than y. That is, I'm integrating over the set of all points in 0, 1 where x is greater than y. Of this function. Now, if x is greater than y, I can just drop the absolute value, plus, and now integrate over the piece where x is less than or equal to y. And in that case, it's y minus x, not x minus y. Now, if you think of the symmetry of the problem, this problem is completely symmetrical because they're IID, and this is a symmetrical function. I could have changed this to y minus x. So really, there's no point in doing two double integrals. Let's just do one double integral and double it. And then we have to do two integrals instead of 4. So that's much nicer. So this is just going to be 2 times the integral of the 2 times the first integral I wrote down. Okay, so just for some, I'm not going to do a lot of double integrals in class, and you won't have to do many double integrals in general in this course, but we have to do a couple of them. So just for practice, let's do this. Basically, the only thing you could mess up is the limits of integration. So let's carefully say, how do we get the correct limits of integration here? The outer limits, since I could have done dy dx, and then it would be different limits of integration. Okay, but I chose, for no particular reason, to just write it as dx dy. So if we write dx dy, the outer limits must refer to y. And we know y goes from 0 to 1. Okay? Now the inner limits, so these outer limits have to just be numbers. As you move inward, the limits can start depending on other variables. So these inner limits can depend on y. In fact, they have to depend on y. Okay? It would not work to go 0 to 1 here because we know x has to be between 0 and 1, but we also know that we're only integrating over x greater than y. So x has to be greater than y, so we would go from y to 1, right? Because x is bigger than y, so it has to start at y. So that's all we have to do, but we do have to be careful. It's easy to mess up the limits of integration. Now this just says do 2 easy integrals. Okay, so it's integral 0 to 1. This inner integral, I integrate x minus y dx, so I'm treating y as a constant. So I would just do x squared over 2 minus y times x. Right? I'm treating y as a constant, and then evaluate this from y to 1. Okay? And so then we just plug in 1 and subtract, plug in y. And then it's just a very, very easy integral, and I won't bore you with all the algebra for that. Just plug in 1, plug in y, and then just integrating a very, very easy integral. And if you simplify that, you get 1/3. So the average distance between two uniforms is 1/3. Let's draw a little picture to see whether that makes intuitive sense to us. So we have this interval 0 to 1, okay, and we're picking 2 uniformly random points in this interval. Let's say there and there. Completely random. But notice that the distance between them is 1/3 because that's 1/3, 2/3, the distance is 1/3. That sort of looks like your stereotypical, if you had to guess something, what would it look like? That might be what you would guess, right? And it works. This actually for me at least, that actually makes the result 1/3 easy to remember, even though that's not a proof, obviously. But that actually does suggest another way to look at this problem, which is I'm picking these two random points, and there's going to be a point on the left and a point on the right. So that suggests reinterpreting this in terms of the max and the min. So another way to look at this would be to let, let's say, m